All right. This video is about discussion on your test one. So we have two questions in your test one. So question one is on a question about control volume, right? So if you read the question, so a standard lab film remover is a typical instrument found in a chemical lab, and the test chamber is 2 meter long, 1 meter wide, and 1.5 meter high. And this researcher is mixing two chemical liquid together, and nitrogen will release into the chamber at a rate of 2 meter cube per minute. So the researcher forget to turn on the ventilator switch before the experimental start. So the gas will accumulate at the top of the chamber. So because nitrogen has less density than air, and it will start to displace the air in the chamber. Assume there's no mixing between air and nitrogen. So the first part A, so we ask you to apply conservation of mass approach, estimate the time rate of change of height of nitrogen in a testing chamber given del H over del T in meter per second. So the unit here, you have to put your answer in meter per second at any distance. Support your answer with a sketch of control volume. So you need to draw a sketch and input all the important dimension. So there's a times mark given. So when you're answering this one, so you should draw something like this. So given all the dimension, 1 meter, 2 meter, 1.5, and then input the control volume with the dashed line. And then the gas of nitrogen is from below, because the chemical was mixed inside here. So your chemicals, your reaction of your chemicals will create nitrogen, and nitrogen will raise to the top of the chamber. So, and then given a H here. Okay. So this diagram will give you some marks there. And by using continuity equation, you write this equation, and then you expand. So for the first term here, control volume here, you have air and nitrogen because there's no mixing. So there's integration for air and integration for nitrogen. And for the second part, the control surface, you have two. So because for nitrogen is go inside, so you get negative, and the air is positive. Air is positive. And air must be conserved, so you write this equation. And then nitrogen also must be conserved, so rate of mass flow rate for nitrogen given by this one, m dot n2 given by this one. All right. And you substitute all the value, you rearrange this equation, you move this term to the right, and rho you move to the left. dV equal to dH dt times the area. So area is 2 times 1, and dH is here, become your dV. And you rearrange everything, all right, in the term of del H over del H. You include all the parameter you have, all right, because you move this one to the left, to the right. Okay. And yeah, and then most of you forget to change your unit. So the answer you need to put in meter per second. So you, at the end, you'll arrive at 0.017 meter per second. So this is for the first part. For the second part, so because this glass cover is 0.75 from the ceiling of the chamber. So calculate the time it takes for the nitrogen to reach the H, which is here, because the nitrogen accumulate here, so it will come to here. So you need to estimate the time. If the researchers stay in the station, stay at that station for 2 minutes, will the researcher have the risk of exposing to high concentration of nitrogen after the experiment start? Explain the reason and give 2 suggestions to avoid this incident. So to reach the depth of 0.75, you just simply take the T equal 0.75 divided by the time that you calculate in section A just now. So the time is 44 seconds, right? And of course, the researcher will expose to the nitrogen because it stay more than 44 seconds. And if you give any two reasonable reason, for example, switch on the ventilator and put on the sign, safety sign, reminder, or put on a mask, all these will give you marks. So this was section B. C, you need to, C is testing you on a deforming control volume. And this one include only the nitrogen accumulating in the chamber. Estimate the time rate change of depth nitrogen del H in meter per second at any distance. So in this case, you need to use the Reynolds transport theorem for moving control volume given by this equation. All right, and then you rearrange according to the statement. And you substitute all the parameter inside there. All right, so negative, negative, because both are moving into the nitrogen, right? Nitrogen are moving in. And then you arrive at this mathematical model. And this one must less than 2 to make this mathematic statement valid. And then you substitute all the value. The answer will be same as section 1, right? So for section C, what we need to see is that, do you understand what equation you need to use for moving control volume with this equation? Yeah. So section C is more on the moving control volume. So that's all for question 1. And you look at question 2, is given by a diagram, a part system with a pump, straight pipe, all the parameter for valve, exits, entrance, and elbow. All right. So a pool of water at Campbell Hiron Strawberry Farm is regulated through a pipe system, which is given below. It's known that the pump supply 2000 watt to the water through the process. All the straight galvanized iron pipe in the system is having internal diameter of 775 mm. So average velocity in the pipe is 5.4 meter per second, and the water temperature pool is 20 degrees C. So you need to be careful when you answer question 2 because the type of material used here is galvanized iron pipe, and unit given here is mm. You need to change into unit SI in meter. And the temperature of the water here is 20 degrees C. So you need to be careful on all these predefined parameter. So the first part, he asks you to determine the loss of head due to friction in horizontal pipe length of L with this section. If the pump 2000 kilowatt, 2000 watt power is used, so we need to find the head loss. So this is actually testing you on the equation of the power for pump. So what is the equation for pump is this one. So you substitute all the value that you find. You find your Q equal to VA. A is the diameter cross section for all the straight pipe. All right, and then you substitute the value inside this equation. At the end, you arrive at 8.5 meter of water. So this is the answer for section A. Quite straightforward. Yeah. For section B, asks you what is the length of the horizon pipe here, right? So it asks you what is the L value if we use the pump of this one. We only consider this section L here, right? So again, you need to determine the type of the flow inside here, you calculate by using Reynolds number given by this equation. And you know that from how you find all this rho value, right? You need to refer to table B.2 at water at 20 degrees C, and your Reynolds number will more than 4,000. You will be in turbulent flow, and you need to use Moody chart to find the friction factor. So this one you can calculate using the roughness for the material given. Then from the chart, you'll find your friction factor equal to 0.235. Right? So if you draw something like this on the Moody chart, you will get some marks. So you start from 4, because your Reynolds number is 4 power 5, right? 4 power 5. So Moody chart here is 1 power 5, so we go to 2, 4. So 4, you draw a straight line up. And then because of your ratio that you calculate is 0.02, so intersection of this one, you move to the left, you get a value here. Okay. So because our Reynolds number is turbulent, so we need to use a dW equation, Darcy equation. Right, you use this one. All right. So you substitute all the value there, you'll find L equal to 18.27 meter. So it is for second part. Huh? All right. Then for section C, yeah, it asks you to calculate the total heat loss in the pipe system. So this is quite straightforward because all the KL value is given. So you start with the energy equation. So section C is asks you to focus on this section. Pump section. All right. So you always start with the energy equation. Because you focus on this section, on the pump section, your Z is not moving, is the same elevation. Velocity is constant inside the pipe was mentioned, right? So V1 equal to V2, you can use two sections, section 1, section 2 here, or section 1, section 2 here also can, because and then you add up all the head loss, right? So this equation, after you apply this boundary condition, you get this one, and you add up all the head loss, right? The entrance, elbow, valve, filter, and acid. And then HL equation given by your KL times the V squared divided by 2G. You add this one, you substitute inside here, you're able to find the change of pressure, right? So your change of pressure will be around 47 kilopascal or 46.88 kilopascal. All right. So that's all for question 1 and question 2 discussion.